Example graphical models. Naive Bayes classifier. For the case of classification, the corresponding graphical model is shown in figure 6.6a with x as the input and c a multinomial variable taking one of k states for the class code. Bayes' rules allows the diagnosis as in the rain and wet grass case we saw in figure 16.1, that is P of C conditional on x is equals to P of C times P of x conditional on C divided by P of x. So if the inputs are independent, we have the graph shown in figure 6.6b, which is called the naive Bayes classifier, because it ignores possible dependencies, namely correlations among the inputs, and reduces a multivariate problem to a group of univariate problems. That is, a P of x conditional on C is equals to pi, multiplying index j starting from 1 to d of P of xj conditional on C. We have discussed the classification for those cases in sections 5.5 and 5.7 for numerical and discrete x respectively. Clustering is also similar, except that the multinomial class indicator variable C is observed in the classification, but the similar variable Z, cluster indicator, is not observed. The E step of the expectation maximization algorithm, section 7.4, uses Bayes' rules to invert the arc and estimates the cluster indicator given the input. Figure 16.6a is a generative model of the process that creates the data. It is as if we first pick a class C at random by sampling from P of C, and then having fixed the C, we pick an X by sampling from P of X conditional on C. Thinking of the data as sampled from a casual generative model that can be visualized as a graph can ease understanding and also inferences in many domains. For example, in the text categorization, generating a text may be thought of as the process where an author decides to write a document on a certain topic and then chooses the set of words accordingly. In bioinformatics, one area among the many where a graphical approach used is the modeling of a phylogenetic tree, namely a directed graph whose leaves are the current species' non-terminal nodes are past ancestors that split into multiple species during a speciation event, and the conditional probabilities depend on the evolutional distance between the species and its ancestor. This is proposed by Jordan in 2004. Hidden Markov models HMM, which we previously discussed in chapter 15, are an example case one where three successive states qt-2, qt-1, qt correspond to three states on a chain in the first order Markov model. The state at time t, qt, depends only on the state at time t-1, qt-1, and given qt-1, qt is independent of qt-2. So P of qt conditioning on qt-1, qt-2 is equals to P of qt conditioning on qt-1. So as given by the state transition probability matrix A, see figure 6.7, each hidden variable generates a discrete observation that is observed as given by the observation probability matrix B. The forward-backward procedure of hidden Markov models is a special case of a belief propagation that we will discuss shortly. Different HMM types can be shown as different graphical models. In figure 16.8a, an input-output HMM is shown. See section 15.9, where there are two separate observed input-output sequences, and there is also a sequence of hidden states. The output observation depends both on the state and also on the input. One can think of this as a B matrix whose elements are not scalars but parameterized functions of the input. This may similarly be seen as a mixture of expert architecture. from section 12.8, whose gating output hidden state depends only on the gating value at the previous time step. Another HMM type that can be easily visualized is a factorial HMM where there are multiple separate hidden sequences that interact to generate a single observation sequence. An example is a pedigree which displays the parent-child relationship. Figure 60.BA models meiosis, where the two sequences correspond to the chromosomes of the father and the mother, which are independent, and at each locus gene, the offspring receives one allele from the father or the other allele from the mother. A coupled HMM shown in figure 16.8c models two parallel but related hidden sequences that generate two parallel observation sequences. For example, in speech recognition, we may have one observed acoustic sequence of uttered words and one observed visual sequence of lip images, each having its hidden states where the two are independent. In a switching HMM shown in figure 60.8d, there are k parallel independent hidden state sequences and the state variables s. At any one time, picks one of them and the chosen one generates the output. That is, we switch between state sequences as we go along. In HMM proper, though the observation may be continuous, state is discrete. In a linear dynamic system, also known as the Kalman filter, both the state and the observation are continuous. In the basic case, state at time t is a linear function of state at time t minus 1 with additive zero mean Gaussian noise, and at each state the observation is another linear function of the state with additive zero mean Gaussian noise. The two linear mappings and the covariances of the two noise sources make up the parameters. All HMM variants we discussed earlier can similarly be generalized to use continuous states. By suitably modifying the graphical model, one can adapt the architecture to the characteristics of the process that generates the data. This process of matching the model to the data is a model selection procedure to best trade off bias and variance. The disadvantage is that exact inferences may no longer be possible on such extended HMMs, and one would need approximation or sampling methods. This is by Gharamani in 2001 and Jordan in 2009. Linear regression. Linear regression can be visualized as a graphical model as shown in figure 16.9. Input x to the t is drawn from a prior p of x, and the dependent variable r to the t depends on the input x. Weights w drawn from a prior parameterized by alpha. That is, p of w is approximately by the normal distribution of parameters 0 and alpha to the inverse times the identity matrix, and the noise epsilon parameterized by beta, i.e. that the p of epsilon is approximately by the normal distribution of parameters 0 and beta to the inverse. Now, the following formula is as follows. P of r to the t conditioning on x to the t, and also w, that is the weight drawn from prior parameterized, is approximately by the normal distributions of w transpose, again using this weight, times x to the t, and with additional parameter beta to the inverse in this normal distribution. And there are n such pairs in the training set, which is shown by the rectangular plate in the figure. Given a new input x prime, the aim is to estimate r prime, which will be expectations of r prime conditioning on x prime and w. The weights w are not given, but they can be estimated using the training set of xr, just as in equation 16.9, where c is the cos of r, and s, where we use the following. P of R conditioning on S is equals to sigma summing for all C of the term P of R C conditioning on S. Note here, right now we introduce C in the conditional probability. And if we expanded the summation formula, that would be P of R conditional on C times P of C conditional on S plus P of R conditional on not C times P of not C conditional on S. Filling in C using S, which we in turn used to estimate R, here we write P of R prime conditional on X prime R and X is equals to the integrations of P of R prime conditional on X prime W times P of W conditional on X R dW. Okay, now the integration can be expanded as follows. Integrate P of R prime conditional on X prime W times P of R conditional on X W times P of W divided by P of R, then integrated by dW, which is approximation, okay, in proportional to the following. The integrations of P of R prime conditional X prime W times pi multiplying for all T of P of R to the T conditional X to the TW times P of W dW, where the second line is due to Bayes' rule and the third line is due to the independence of instances in the training set.